Niaje wase. No one said it's going to be easy. We started off on a slow start. But this is YouTube. It takes commitment and being consistent. Yeah. So, but write to me, give me a like, pay comment, just to know that I'm not alone and I'm not speaking to myself. This is what I have for you today. So this is an adapter. It's a phone adapter. It's those switching power supplies with PD charging and fast charging. So this one was from a phone. I've not looked at it before, so I wanted us to look at it together, but it's not working. So as you can see, the cover itself, matumbo yote iko nje. Yeah. Just to go around what this is, you can see we have a bit of caps here, capacitors. Here, this is the AC part of it. I can see a fuse, some common mode inductor. Then here, maybe it's a bridge. I can't tell. We have to take all this resin out. Maybe now these are the DC, high voltage capacitors. We have a transformer and we have other smaller caps. So these probably are on the output of the transformer. And inside there, if my phone can focus, we have something like a chip here. Maybe this is what is communicating with your phone to request for more voltage. And this has one USB-C output. Take the resin out so that we can investigate further. So let me try and get this out of the way so that we can see what we are working with. As you can see, we have an area here that is blackened. Maybe something is burnt on this area. So maybe this is what is wrong with it. Let me continue to take all this resin out so that we can be able to see what's going on. We are making progress. As you can see, I'm trying to get most of it out, but there's a bit of an issue on this area, the burnt area. There are pieces of copper is coming out. So I have to get on the microscope. Then let me do this on the microscope, then I'll come and show you the results. This is day 2. Yesterday, I was running out of light, so we had to cut. So, but I did a very good job at cleaning out all the resin, as you can see. If my camera can focus. Yeah. I also created a circuit for you guys, a simple schematic. Yeah, this one. So we have to go under the microscope again so that I can be able to show you how everything comes together. I also want to apologize for the changes in sound. I changed a microphone. I'm using a different microphone now, and my computer, all the ports they are taken here. That's how insane it is. But look what I've been working on. Let me show you that one. Can you see it? Yeah.
that meter window. This is what I've been busy doing. So now we can be able to see all the voltages from the meter directly on a window on the screen. So I'm happy about that. So let's go on the microscope. Maybe it may look complicated, but I'll guide you through the circuit that I just illustrated. So we have the AC coming in on these two conductors, yeah, live and neutral. On one conductor, it goes through a fuse, which is this one. This brown rectangular thing is a fuse. Then the other conductor goes through this component here. This is NTC, negative temperature thermistor. Yeah, goes through it here. Then from the thermistor, it goes to the input of this choke, which is this inductor, as you can see, this one. So the output of that choke, so this choke is an EMI filter, yeah. It blocks high frequency currents. Then from the output of the choke, we go to the input of the bridge rectifier, which is this rectangular thing here. These are 4 diodes actually. They're in just one package to make a full bridge rectifier. So these are the 2 AC in, and then the output of the bridge here and here. This is the positive from the output of the bridge goes to this capacitor, which is this one. You can see this is the negative of the capacitor, and on the other point is the positive. So it goes here to the positive. Then the negative of this cap is connected to the positive of this other cap, which is this other second capacitor. And these two capacitors, they're in series, right? As you can see on my schematic here. Then also from the positive of this cap, it goes to this thing here that got me confused a little bit what it was, which is this device here. It looks like a coil here or a ferrite bead. I don't understand, but it has very low resistance, which is, sorry, it's these 2 points here. Yeah, positive here goes to the positive of these other pairs, which is these two capacitors. So we have the positive, the negative, positive, and negative here. And this one goes directly to a transformer, yeah. And we have a broken track here. So things happened here. So I was a bit confused why a negative was going to a transformer, but maybe this is part of another auxiliary winding. So the positive from here, yeah, this pair goes to this point of the primary winding of the transformer, yeah. So from here to here we have like 0 ohms, so it goes here. Then this other end of the primary winding goes through this MOSFET. You can see goes to the what is this, the drain of the MOSFET, and the source of the MOSFET is connected through this shunt. It's a low ohm resistance to the ground or the negative of the capacitor. So this is N channel high voltage, high switching MOSFET. This is its drain. This is sorry, this is its gate. This is the drain, and this is the source. Yeah. So the drain, this and these 2 points, they are the same here. So this is also the drain, right? So we have a bit going on here. This is where the damage was, and the shunt, this low resistance actually burnt. As you can see, there were 2 in parallel, so one of them got burnt away and took the copper traces with it. And this point I was not understanding, because this is a huge track, you know, it cannot easily be damaged by high current, and it's part of winding of the transformer. So if there was high current, the transformer probably would have burnt, but not the track. You can see there's a disconnection here. So what I think, maybe I was using a lot of force here when I was taking this thing apart, and I broke this track. But let's proceed. I've shown you most of the input circuit, the high voltage capacitors, the EMI filters, the switching MOSFET, the shunt, also the auxiliary winding, which is from here to here. So this is what powers this part of the control logic or the switching PWM logic. So we have this IC here. Probably this is a voltage regulator because I can see one track of it goes here. You can see it goes to this cap, which is this small one. I'm not sure you can see because I could not take all the resin out, which is this capacitor. So this capacitor is what is providing voltage for this PWM IC that switches this MOSFET. So this is a very small cap as you have seen compared to these other big caps. So this has low voltage on it. Probably there are diodes here and capacitors that are filtering or rectifying the auxiliary voltage so that it can power this IC. So probably this is the voltage regulator part for the IC. This is the PWM IC. Again, as I said, driving this MOSFET. We have a bunch of caps here, some maybe for setting the oscillation and frequency, and a bunch of resistors here. Then we have an optocoupler here. This is what links the primary to the secondary, and it changes. So this PWM IC changes the duty cycles depending on how the optocoupler behaves. Yeah, I'll explain that later. Then you can see this big isolation gap here, yeah, that is isolating the primary and the secondary. So this is the right side is the primary, the high voltage side, and the left side is the secondary, the low voltage side. And you can see here the two outputs from the transformer. So this is the low voltage from the transformer goes through this MOSFET here, N-channel MOSFET. So this is the rectifier diode. Actually, they call it a synchronous rectifier. So instead of using a diode as a normal flyback, they're using a N-channel MOSFET. So an N-channel MOSFET, when it's on, has very low on-state resistance here compared to a diode. A diode, a Schottky diode can drop 0.2 or 0.3 or 5 volts, but MOSFET, when it's on, it has almost no drop. It doesn't drop any voltage. So at high power, it's very efficient to use MOSFET in replacement of a diode. And on the other side of the board, you can see a bit of logic here, a chip. This one probably is what is driving this MOSFET here. Then as we proceed, you can see now the voltage reaches on these two capacitors. Yeah, this and this. So these are the output caps. You can see the red marking area. This is the negative. So the negative is on this end. Yeah, and the positive goes through another transistor, MOSFET probably here. And this is a channel N also. You can see this is the source and this end is the drain, and the body diode is connected between the source and the drain. So it makes sense this is an N-channel MOSFET because it's blocking voltage from going through this side. And as you can see, on the other end also, there is a chip here. So this is the PWM IC. This is what is communicating. No, sorry. This is the PD controller. Yeah. This is what has all the protocols for charging. So this is what communicates with your devices when you plug them on the charging port. So the devices can be able to request for a certain voltage, a certain current. So they communicate with this IC. And now this IC is responsible for driving this MOSFET. So once communication has been established with your phone and they agree on a certain voltage, the IC now enables this MOSFET, and the voltage that appears on these capacitors now can go to the output here. So there is also a current sensor here. You can see this is a very low resistance shunt. So probably also the IC is monitoring the current that is going to the output. Now that you have seen what's going on, we need to do a few tests, yeah, because we have seen a few damage here on this resistor, and probably even the MOSFET is burnt. If this resistor is burnt, then it means there was a high current through the MOSFET. Yeah, so we have to do a few tests to make sure that the components are working before we can proceed with repair. You know, some repairs, they cannot be done if you cannot ascertain what is going on. So I'm going to show you my fancy microscope window, or sorry, my multimeter window that I've just shown you, which is this one. Yeah, so you're going to do a beep test resistance. Beep, that one. So my probes, yeah, you can hear the beep. So we are going to start with checking the fuse. So from here to, sorry, you can't see, from here to here, yeah, the fuse is blown. What about the NTC? From here to here, yeah, the NTC is alright, we have 7 ohms. Then goes to the common mode inductor. From here to here, it's fine. Here to here, it's also fine. Then goes to the AC input of the bridge rectifier. Positive lead to one AC input, and on the output, yeah, you can see voltage drop of one diode. Then to the other AC output, nothing. Yeah, that's what we want to see. Then I'm going to switch my meter, my probe, to the other AC input, and here we are getting the voltage drop of a diode, and here we should get nothing. Yeah, now I'm going to switch my probe, the red probe, to the output. Yeah, on the output we should get a reading on to the AC input. Nothing there, nothing there. Now I'm going to switch to the negative output of the bridge. We should get only ones, yeah, here and here, yeah, and we should not get any measurements from here to here. Then do we have a short on the output of the bridge? Probably not. From here to here, nothing, so that's fine. Then goes through the ferrite bead. The ferrite bead is okay. Yeah, we have a beep. Then this cap is okay, and also this cap is okay. What about the two caps in series? Yeah, they are both fine. Then it goes to what? We are looking at the transformer. So we have the primary winding here. Yeah, the primary winding probably is fine. That's very low DC resistance, so that's okay. Goes to the drain of the MOSFET. The MOSFET, is it okay? Drain to, no. What? Drain to gate. Drain to gate is shorted. Let's switch to resistance so that you can be able to see the actual home reading. Yeah, from drain is here to get 0 resistance. No, it's not 88. That's a bit sus. What about drain to get to source? 86. What about drain to source? 0. Here, it should not be 0, especially if the MOSFET is off. Yeah, so probably we have a burnt MOSFET here. This is what caused the current sense resistors here to blow. If I check the resistance, it's like OL, so very high resistance, like 22 mega ohms. So this should probably be very low, yeah, less than half an ohm, so that we can measure the current. So this resistor is blown, this MOSFET is also blown, and this track. First, maybe I should remove this MOSFET and see if the resistance between drain and source is gone. So that will give us an idea, maybe the IC also survived. So let's take that MOSFET out. Now we are checking together again the same point, drain and gate 0 like 5 mega ohm. So the 80 ohms resistance is gone. What about drain and source? 6 mega ohm. Yeah, so our short is gone. Yeah, probably this transistor is damaged. Between drain and gate, it's measuring around 190 ohms, so that is not good. And the resistance is going down because the transistor is hot, so as it cools down, the resistance is going down. What about drain to source? Yeah, drain to source, it's shorted, so this is what failed. Let's just do a few other tests, just so that we know no other component was affected. So we have the regulator here with the capacitor here. I'm checking the resistance on the capacitor. The capacitor is okay. So probably what you want to be checking is the cap. So the cap, they sit on a voltage rail. Yeah. So if a cap is shorted, then it will give you a good idea that something on that voltage rail is shorted. So this cap is okay. So probably maybe the voltage regulator here and the chip, maybe they are fine. I'm going to check ground. This is ground. Yeah, this is ground and most pins of the IC. So the resistance is good. If we see a short on many pins with ground, then probably this is ground, probably. And you can see most of the pins, they are not beeping, so maybe our PWM IC survived. The coupler can check between these other ends are the emitter and collector of the optocoupler. So probably you'll see the voltage drop of one diode. This end, nothing. What about this other end? Yeah, 0.6, that's good. Then this other end of the optocoupler has the LED. So this is the anode. So you put your positive lead on that pin and it will give you about a 1 volt. Probably it's 1 volt. Yeah, 1 volt. So this is an infrared red LED. So it has a very low voltage drop. So this optocoupler is working. What about the MOSFET, the synchronous MOSFET? Now this other end is the voltage drop of the diode. Yeah, this is the source and this is the drain. Yeah, we can see 1.15. What about the way I measured before? Yeah, this was capacitor charging. So I believe everything is fine from the output as far as I'm seeing. So we are again going to check the voltage drop of the body diode, which is from source to drain. Yeah, 0.47. So it's okay. What about drain to source? You should see some capacitor charging and it's going up, so this probably is fine. So our issue here is this track, this current sense resistor, this MOSFET, and the fuse. So let me try and see if we can patch this up and maybe find, because I don't have this SMD high voltage MOSFET, I'll have to find something maybe that is, we can just test this on the bench and see if it's going to work, and I'll order the right MOSFET if actually it works. I'm going to thin this just a bit because I don't have this current sense resistor. I'm just going to use a wire. A wire is just going to work fine. Just a thin wire so that even if the current is so high, it will burn instead of our MOSFET burning. So that's fine. And also the fuse. All these I'm going to use just a small wire. The fuse is also fine with a wire because I'm going to use a series bulb. So if the current goes very high, our bulb will protect everything. This is what we are going to use. This is a N-channel high voltage MOSFET. It's a 12 and 60 here. So what you have to keep in mind is this adapter is not a gallium nitrate. So gallium nitrate is a whole different ball game. So this uses just a normal NPN transistor. So we'll just try with this one and see what happens. Yeah, if it works, we know we are on the right channel. This is a big package. This is like a 220. Yeah, you can see it's so big. So what you have to do is just bend these wires just a little bit to get the right connections. Yeah, that's what I'm going to do. I mean, we are not going to win any awards in the looks department, but this is just for testing purposes. Yeah. So what I want to check now, if we have any shots, you can see all the pins make the right connections. So we have the gate here to the gate, the collector, which is this one, and this is the source. So between the gate and the source, yeah, like 8 kilo ohm, that's fine. Gate and drain, very high resistance, like 3.8 mega ohms. Drain and source, again very high resistance, 4 mega ohm. So I believe we can go ahead and test. I'm going to put my safety glasses on, and it's on. Okay, no explosions so far, and it's on. Yeah, and something is still shorted. The bulb is glowing. Checking again from drain to gate. 100 kilo ohms, drain to source 5 kilo. So it's the MOSFET that shorted. From drain to source. Yeah, the MOSFET is gone. So I don't understand. So either we have the wrong MOSFET here, or the PWM IC is actually damaged and it's destroying our MOSFET. Usually what happens, because the current sensor is directly connected to the control IC, when the sensor blows here and the MOSFET is shorted, you end up having high voltage here through the primary, through the MOSFET, and that goes to the IC. And this is what kills the IC. So let me check if I can get a different IC, the same one, a new one, and also buy the right MOSFET for this power supply and check if it's going to work. It will take about 2 weeks maybe to get those parts, but I'm sure you learned something, and also like and share, because if I see most of you they are interested in this kind of videos, I'll be sure to update. Maybe twice in a week we can create something nice for the channel. So like, share, and subscribe. I'll see you again soon. Bye.